All right, kids. So let's talk about the early atom hiding from whatever it is today. So this, if you ever want your book, is chapter 3 in your book. There it is, chapter 3. Okay. All right. So the history of the atoms goes all the way back to 400 BC, where the Greek philosopher Democritus came up with the idea that if you cut something like a marble, you can cut it in half, and then you can cut that in half, and then you can cut that in half, and you can keep cutting something until the point where you couldn't cut it anymore. So this was just philosophy, just him hanging out by the pool, thinking about what happens if you cut this and whatnot. So he called these particles that you could no longer cut atomos, and that is where atoms are derived from, the word atoms, and atomos means indivisible. So this wasn't science, this was philosophy. This was just a guy hanging out, thinking about things during the high times of Greece. So then John Dalton, not to be confused with Andy Dalton, John Dalton, who looks more like, who does that look like? Looks like a guy on ESPN. Can't remember his name. Not Buster Olney. Anyway, he established the first atomic theory. So this is actual science. So theory being something that seems to be true. There's a lot of evidence pointing toward it, but hasn't been proven absolutely. So his atomic theory came up with that all matter is composed of small particles called atoms. So he had enough evidence to put this theory together, and that atoms cannot be divided further, just like Democritus came up with. Then he said each element has identical atoms. So all carbon atoms are the same, all gold atoms are the same, all silver atoms are the same, different from each other, but the same for any one element. So if you have an helium atom and you have another helium atom, they're identical, and that would be identical to a third helium atom. That was what his theory was. Different elements have different atoms, so helium would not be like carbon, but and carbon would not be like gold, and that in chemical reactions, atoms are combined, separated, or rearranged. So this was his atomic theory, and basically he came up with the idea, as Democritus came up with, basically that there's some kind of sphere that you can't break up anymore, and it's indivisible, and it's called an atom. So basically, it's just the world is made up of tiny little balls, and the little balls hang out together. All right. Now comes J.J. Thomson, 1897. I don't even know what the 1808 was the other one. So almost 100 years later, he's playing around with atoms. We've figured out how to have electrons move around. Electrons were sort of electricity, and he thought, all right, well, what is the charge of electricity? Is it positive? Is it negative? Is it no charge? So he was the one who figured out that electrons have a negative charge and they have insignificant mass. So what he did was he shot electricity, so electrons, a stream of electrons, through an area that had a charge plate positive and a charge plate negative. And so the theory was that if you shoot electrons through this, if they had no charge, then they wouldn't be attracted to either plate and they would go straight. So here where B is, that's what would happen. If they had a negative charge, they would have been attracted to the positive charge plate, and you would have something where A is. And if they had a positive charge, they would be attracted to the negatively charged plate, so you'd have C. So basically, if you shoot electrons through this charged area, if there's no charge, they'd go to B. If they had a negative charge, they'd be attracted to the positive charge and go to A. If they had a positive charge, they'd be attracted to a negative charge and they go to C. And then this was a screen that would show you whether or not it was being hit by electrons or not. So it turns out when he does his experiment, he does not get anything there at C, so they're definitely not positive, and he got nothing at B, so therefore they definitely not no charge. Hence, they were negative. He figured out the insignificant mass because you can manipulate how high something moves up this plate based on the charge of this positive. So you make this more positively charged, and this would go up more based on its in a ratio to its mass. So if it had a heavy mass, it might only go up a little, and then you make it super hard, super super attractive, and it might go, if it's heavy, it wouldn't go up as high as something that was very light, which would go up much higher. So he was able to figure out that electrons have insignificant mass because they moved pretty much to the top of the plate regardless of how much pull there was. And he figured out the negative charge because they were attracted to the positive plate. So Thomson, this guy J.J. Thomson, comes up with what's called the plum pudding model, which in current terms is more like a chocolate chip cookie model, where you have some positive matrix of dough and these negative electrons stuck in like chocolate chips. But back in J.J. Thomson's day, plum pudding was the chocolate chip cookie of the era. So he used that. But nowadays, since nobody knows what plum pudding is, we call it the chocolate chip cookie model. All right, then Ernest Rutherford from the Giant Stadium, Rutherford's. I don't know that that's true. But he said, hey, everybody, the atom is not like this. It has a nucleus. The atom is mostly empty space, and there is a very dense nucleus. So the experiment he did to prove this, I will, or I have already, depending on when you're listening to this, I built a model of this experiment. So basically what he did was he wanted to take a piece of gold foil and shoot alpha particles, which were considered pretty dense particles. They're actually helium nuclei, I believe. And his feeling was that if it was just chocolate chip cookie that was between one end and the other, it would just burst right through that, no problem. And that's what he anticipated. So here's this gold foil. He made it as super thin as possible, and he shot these alpha particles through. And the feeling was the alpha particles would just go straight on through, because if it was only chocolate chip cookie holding them back, they were going to burst on through. Well, what it turned out happening was some of them sort of veered off to sides, and then some bounced back, which he's like, what? How do you bounce back? What exactly is in this cookie that's making things bounce back? So that's why he came up with this idea of a dense nucleus, that there was something in there that was so dense that when you shot an alpha particle in it, it would bounce off. So this is what he thought would happen. There'd just be sort of these chocolate chip cookie things, and everything would just go flying through this very thin gold foil, these alpha particles. But what really happened was some went through, some sort of veered off, like they were kind of glancing off something or attracted to something perhaps, and then some were bouncing straight back like they hit something. And that was not what he expected. And we'll play with something in class. So now the model of an atom, because of Rutherford, is that there's a very dense positively charged nucleus, and then these electrons are flying around, but it's mostly empty space. So while everything can mostly go through, there is the occasional thing that bounces back. All right. Moving on to the Heisenbergs, which Heisenberg and Schrodinger, which I bring up just because it's fun what they talk about. So they developed math probability. So this isn't even observation anymore. This is just a math function that they kept getting the same answer over and over again. And that determined that there were regions where electrons were likely found. So there is this dense nucleus that contains protons and neutrons. And then they said where the electrons are can be established by this math function, which will tell you the regions of high probability. And they called these regions clouds. These electrons were in what they called clouds. So let's think about that. So here you have their little probability function, and it's a very high probability that you'll see electrons here. And then as you go away, they go down, down, down. And then there's a very low probability. So you see how it forms sort of a cloud. There's a lot of electrons in here. There's very few out there. So you could think of it as there's a high probability you'll see students in the school during the school day. There's less of a probability as you get further and further away that you'll see these students in the school. So you can sort of establish a place where you'll find the majority of electrons in an atom, just like you can define a place where you have a high probability of finding the majority of students at the school. So then after some dead period, another area will show up and there will be a high probability again. And that's the second sort of shell. So there's this first area with high probability, then it kind of dies off, and then it picks up again. and then it dies off, and then it picks up again. So there's multiple areas of high probability. So we call those shells. And then there's these areas where you're very low probability of finding electrons, and we call those nodes. So sort of the areas where you're less likely to find electrons are nodes, and the areas where you're very likely to find electrons are shells or clouds. Electron cloud model is what this was called. And this is currently how we understand the atom, which doesn't mean that that's what's actually happening. It just means that's how we understand it now. And that's sort of the point of, yeah, the electron cloud is where the electrons are known to be. I'm like reading this with you. It's like, oh, what does that say? The point of all this is that we teach you in science what we understand now, but we could be, and probably are at some point of our understanding, like Dalton or like Thomson, where things can happen where we learn more and then we have to alter our understanding of something. So you should never sort of sleep on your knowledge of science as the be all end all. It's always developing, it's always moving on. There you go. So this is sort of a picture to demonstrate the fact that we started thinking all atoms were these little balls stuck together, and then the balls became mostly empty space, and then it became just mathematical functions that are keeping electrons away from each other. And you really start wondering, what am I walking on anymore? I don't know if that works anymore. Okay, James Chadwick. That came to me like in a dream. I don't know if that works anymore. It's a good picture though. All right. Chadwick, he used plutonium alpha particles, proved that nuclearly neutral particles existed and have similar mass to that of a proton. He called those a neutron. I will never ask you these dates. I don't even know if I'll ask you what his name was, but we now know that neutrons have no charge and that they're in the nucleus. So what we know now, besides what Dalton thought, atoms have a combination of smaller particles. They're these subparticles, these electrons, these protons, these neutrons. J.J. Thomson's cathode ray tube provided the basis for the discovery of an electron. That's important to know. Rutherford established that the atom is mostly empty space with a dense and positively charged nucleus. And the nucleus is made of protons and neutrons surrounded by electrons in a cloud. So that's our understanding there. So Dalton's theory is revised because atoms contain subatomic particles. He thought the atom was just one thing. And they're mostly empty space. So yeah, supposedly, if the RBC center were, if that's what it's called still, I think that's what it's called, where the Hurricanes play across the street, I don't think it's called that anymore. Anyway, if the nucleus were at the center court, it would be the size of a grape, and the electrons would be the rest of the stadium. So that's how much empty space there is in an atom when you think about how big the nucleus is compared to the rest of the atom, which is kind of why, honestly, I dislike this picture. I can't find a better picture, but this makes it seem like everything's bouncing off. But that would not be the case if you were trying to hit a grape in the RBC center, and the RBC center was the size of the entire atom. So think on that a minute. Anyway, and electrons don't orbit. It's more like preschoolers just flying around in randomness. But the randomness has some high probability of areas where you'd find them. Even though this picture makes it look like they fly in orbits, they don't really fly in orbits. All right, there you go. That is what we're going to call the history of the atom, part 1.